This week we will study linear momentum on example of one-dimensional elastic and inelastic collision. Linear momentum is defined as the product of the mass and velocity of the object. P is equal m times v. The units of linear momentum are simply the units of the mass times the units of velocity, and that is kilogram meters per second. It is important to note that the constant linear momentum p is the momentum of the object of the mass m that is moving on a straight line with a velocity v. Momentum is a vector with magnitude and direction because velocity is a vector with a magnitude and direction. The magnitude of linear momentum depends on mass of the object as well as the speed. Since momentum is a vector, the total momentum of a system of objects is the vector sum of the momenta of all objects. P total is equal to P1 plus P2 plus P3 and so on, as many objects as you have. To illustrate the vector nature of momentum and linear momentum addition, we will use an example from your textbook. We are going to add the momenta for 2 ducks and a goose. At a city park, a person throws some bread into a duck pond. 2 4-kilogram ducks and a 9-kilogram goose paddle rapidly towards the bread, as shown in this sketch. If the ducks swim at 1.10 meters per second and the goose swims with a speed of 1.30 meters per second, find the magnitude and the direction of the total momentum of the 3 birds. So first, let's go ahead and picture the problem. In our sketch, we place the origin where the bread floats on the water. Note that the duck 1 swims in the positive x direction, duck 2 swims in the negative y direction, and the goose swims in a positive y direction. Therefore, the momentum for the duck 1 will be given by this equation. PD1 is equal mass of the duck times the velocity, and the direction is a positive x-axis. Multiplying mass and velocity, we are going to get that the momentum of the duck 1 is 4.40 kilogram meters per second in the positive x direction. The momenta for the duck 2 is, since the duck 2 is moving into the negative y direction, it's going to be a negative mass of the duck 2 times her velocity. And then we will get that the duck 2 has a same magnitude of momenta as a duck 1, only into the negative y direction. And the momenta of the goose is going to be given by this equation, mass of the goose times the velocity, and the goose is moving into the positive y direction. So the momentum has a magnitude 11.7 kilogram meters per second into the positive y direction. The total momentum, P total, is the sum of the momenta for the first duck, second duck, and the goose, and it's going to point with the angle theta relative to the positive x-axis. So now when we have the magnitudes and the direction for the momenta for duck number 1, duck number 2, and for the goose, we can find the total momentum. So by adding the momentum of the duck 1, I had the only momentum in the positive x-axis. So x component of the total momentum is going to be equal to 4.4 kilogram meters per second. And then duck number 2 and goose, they had a momentum into the y direction. Duck number 2 into the negative y direction, and the goose into the positive y direction. By adding these two, we are going to get the component of the total momenta in y direction, and it's going to be equal to 7.30 kilograms meters per second. So now you remember from the experiment when you did the vector addition, the magnitude of the total momenta is going to be a square root of the components squared, and then we get the magnitude of the total momenta is going to be equal to 8.52 kilogram meters per second. The direction of the total momentum is going to be given by this equation, is the inverse tangent of the y component of the vector divided by the x component of the vector, and we get that the direction of the total momenta is going to be 58.9 degrees. Here you have to remember one thing. The momentum of each bird depends only on its mass and velocity. It is independent on the bird's location. In addition, we observed that the magnitude of the total momentum is less than the sum of the magnitudes of each bird's momentum individually. This is generally the case when dealing with vector addition. The only exception is when all vectors point into the same direction. Now we will talk about the momentum and Newton's second law. A couple of weeks ago, we introduced the Newton's second law, which states that sum of all forces acting on an object is equal to the mass of that object times the acceleration of the object. This equation is valid only for objects that have a constant mass. The most general version of this law that holds for even if the mass is changing is given by this expression. The net force acting on an object is equal to the change in its momentum divided by the time interval during which the change occurs. The net force is a rate of the change in momentum in time. To show the connection between these two expressions, we have to consider change in momentum. Remember that momentum is mass times the velocity. Then the change in momentum is going to be given by the final momentum minus initial momentum. We can write down what the final momentum is. It's the final mass times velocity final, minus initial momentum is initial mass times the velocity initial. If the mass is constant, the mass final is equal to the mass initial, it's equal to the mass. It follows that the change in momentum is given by the mass times the change in velocity. From here, the Newton's second law for the object of the constant mass is given by sum of all forces is equal to the change in momentum over a period of time, and that's equal to the mass times the change in velocity over a period of time. And since acceleration is the rate of change of velocity with time, this equation reduces to the sum of all forces acting on object is equal to the change of momenta over a period of time, and that's equal to the mass of the object times the acceleration of the object. From here, we see that two statements are equivalent if the mass is constant. It is important to remember that this term is a general form of Newton's second law and is valid no matter how the mass may change or may not change. If there is no net external forces acting on a system of several masses, the momentum remains constant. This means that the change in momentum is equal to 0, which means that initial momentum of the system is equal to the final momentum of the system. Interaction between the different masses may redistribute the momentum, but the momentum after the interaction is the same as the momentum before interaction. The object of this experiment is to study the conservation of momentum principle as it applies to collisions of two dynamic carts on a track. We will consider a collision of a target cart of mass m initially at rest and a projectile cart of mass small m initially moving with velocity vi. The collision is such that kinetic energy is conserved, which means that the collision is elastic. After the collision, the projectile will move with velocity v final and the target will move with a velocity capital Vf. The equation for conservation of momentum is given by P initial is equal to P final. So before the collision, the target was at rest, so the momentum of the target was 0, and the projectile was moving with initial velocity vi, so the momentum of the projectile is mass times vector of initial velocity. And then after the collision, both of the objects were moving and both of them contributed to a momentum of the system. So the momentum of the projectile is mass of the projectile times the final velocity of the projectile, and then plus mass of the target plus final velocity of the target. Since the collision is happening in the direction of the positive x-axis, we can write the magnitudes for the momenta. This equation will reduce to mass of the projectile times the initial speed of the projectile is equal to the mass of the projectile, final speed of the projectile, plus mass of the target times the final speed of the target. Since this collision is an elastic collision, the kinetic energy is conserved, which means that the initial kinetic energy is equal to the final kinetic energy. So then the equation for the conservation of kinetic energy is given by this term. Is the kinetic energy of the projectile before the collision, and it's equal to the sum of the kinetic energies for the projectile and target after the collision. Now we will move on to the conservation of linear momentum for the inelastic collision. So before the collision, again, the target that has a mass capital M is at rest and the projectile moved with initial velocity vi. If the projectile and target cards stick together so that the collision is completely inelastic, the conservation of momentum principle will give the following. Initial momentum is equal to the final momentum. So before collision, only projectile had a momentum. After the collision, two objects stuck together and they moved with final velocity. So the momentum after collision is the sum of the masses of two objects times the final velocity of the combined object. Now, same as before, since the collision is happening in the direction of the positive x-axis, we can look at the only magnitudes. So mass of the projectile times the initial speed of the projectile is going to be equal to the sum of the masses of two objects times the final velocity of the combined object. The kinetic energy for inelastic collision is not conserved, which means that the initial kinetic energy is not equal to the final kinetic energy. Since the kinetic energy for completely inelastic collision is not conserved, we can calculate a fractional change in kinetic energy, which is given by this term. It is a change in kinetic energy divided by the initial value for the kinetic energy. In physics, you can calculate a fractional change for any quantity that is not conserved by using this equation. It is the change in that quantity divided by the initial value of that quantity. So now let me ask you this. What do you think? For ideally elastic collision, how much is the fractional change in kinetic energy? You're correct. For ideally elastic collision, the kinetic energy is conserved, which means that the initial kinetic energy is equal to the final kinetic energy. So then change in kinetic energy is zero. So then the fractional change in kinetic energy will be zero. Now we will go ahead and calculate how much is the fractional change in kinetic energy for completely inelastic collision. So we know that the fractional change in kinetic energy is given by this equation. It is the change in kinetic energy divided by initial kinetic energy. From here you can write the equations for the kinetic energies. So the final kinetic energy is going to be 1/2 mass of the combined object times the speed of that object squared. Initial kinetic energy is 1/2 mass of the projectile, initial speed of the projectile squared, and then divided by the initial kinetic energy. Now here you have one equation with two unknowns, final velocity of the combined object and initial velocity of the projectile. From the equation for the conservation of momentum for completely inelastic collision, you can express the final velocity of the combined object, and it's given by this term. Now, by plugging in this term back to the equation for the fractional change and cutting off 1/2 here, we get this term. So now we can remove initial velocities because this is a term that's appearing in all three terms, right? And then we can cut this term here, m plus m, with this squared here, and then this reduces to this term, and then from here we get m divided by m plus capital M minus 1. Now adding these two fractions together, we are going to get this term, and then finally we are going to get that for completely inelastic collision, the fractional change in kinetic energy is equal to negative mass of the target divided by the combined mass of the two objects together. Next, I will show you how to collect the data for this week's experiment. So this is the setup for this week's lab. You have a track, same that you used before. You have a projectile cart that has this plunger on the end. The target cart is the cart that has two screws on the top. One side of the target cart has the magnets, and this side is going to be used for elastic collision. And another side of the target cart has a Velcro. So this side will be used for inelastic collisions when two of these carts stick together. And then you have a mass that you will use, that you will add to a projectile cart for the case of elastic collision. This time we're going to use two smart pulleys and two photo gates because we need to record the position of the target cart and position of the projectile cart. Also, you have paper clips. Paper clips will be used to overcome the friction between the track and the carts. So before you start, use the balance in the lab to measure the mass of the added mass, to measure the mass of the projectile and mass of the target. Once you're done with that, you're going to level your track by adjusting these screws on the back feet and the front feet. Okay, once you get track entirely leveled, you're good to start the experiment. So same as before, first we will collect the data, and then after that I will show you how to analyze the data. So you're going to place a projectile cart with the plunger on the end, and then guide the thread across the first pulley. This is the pulley that you have been using so far in the previous weeks. Okay, and then you will add a couple of paper clips, just enough to overcome the friction. Same as before, you have to make sure that the thread is across the pulley. Okay, so now we will add a projectile cart. On one side of the cart we have this Velcro that will be used to stick these two carts together. And then if you turn the cart around, there will be a magnet on this side of the cart, target cart, that will be used for elastic collision. Okay, so the first part of the experiment we're going to do the elastic collision. So make sure that the thread on the cart is on this front screw now for the target cart. Then guide the thread through this hole here on the post. And then across the front pulley. And same as for the projectile cart, add a couple of paper clips to overcome the kinetic friction between the cart and the track. So you see the thread for the target cart is going through this post here, through this hole, and then straight across the pulley here. And it has to be on the front screw for the target cart. So as I said, first we are going to do elastic collision. So for elastic collision, we are going to add the this mass to the projectile cart. Once you're ready, you are going to log into a student account, and then from the start menu, open the folder 1101 and then choose experiment number 11, conservation of momentum in one dimension. So now you are going to give a push to this projectile cart and then record the position versus time. And then press stop. So now when you have the data recorded, one thing you have to remember here, the photo gate that records a position of the projectile is connected to a channel 1 on the science workshop, and then channel 2 is connected to a photo gate that records a position of the target. So on your Data Studio, X1 will correspond to a projectile and X2 will correspond to a target. So now, once you're done collecting data for elastic collision, we are going to move on to collect the data for inelastic collision. So just turn this cart, change the position of the thread. So thread is on the front screw, and then again bring the target somewhere around the center of the track, and then repeat the same motion, this time without the added mass to the projectile. So what will happen this time, projectile and target will stick together and they will continue moving after the collision as a one big object. Okay, so same as before. Give it a push and stop once it reaches the end. So once you're done with taking the data, you're going to return the table to original setup. So remove the paper clips, place the projectile, and same for the cart, and leave the table in exactly the same condition you found it when you walked into the lab. Now I will show you how to do a data analysis on the data that we just obtained. This part is on data analysis. We already recorded the data using the Data Studio. So run 1 is a elastic collision and run number 2 is inelastic collision. If you remember, we said that X1 records the data for the projectile and X2 records the data for the target. Now we will take run 1 for elastic collision for the projectile, drag it down to a graph, and plot a position versus time for the projectile. So as you can see, the slope after the collision for the projectile changes, and this is where the collision happened. Now we will plot on the same graph run number 1 for the X2, which is a data for the position versus time for the target. So if you remember, initially the target was at rest, projectile is moving with some initial velocity. This is where the collision happens, and then the momentum is transferred to a target and target continues moving, and then after some time projectile will stop. In order to calculate the momentum and to check if the kinetic energy is conserved and if the conservation of momentum holds, we need to find the velocity for the projectile before collision and after collision, and velocity for the target after the collision. So simply we are going to highlight here run number 1, the red curve, which is a curve for the projectile. Then we are going to highlight the part of the data that's not close to the collision and to the beginning of the data collection, and we will use a linear fit and obtain the velocity. So this is initial velocity for the projectile cart before the collision. You will record this to your laboratory manual. We will highlight run number 1 for the green curve. This is a curve for the target after the collision. Then go ahead and highlight the portion of the data that is away from the point of the collision, and then use the linear fit and get the velocity. The velocity you obtained is a final velocity for the target. You will record this to your laboratory manual. Now you're going to highlight run number 1 and then select a couple of the points after the collision for the projectile and use the linear fit to obtain the final velocity of the projectile after the collision. Please record these values to your laboratory manual. Now you're going to print this graph. Since in Data Studio you cannot take a multiple slopes of the same curve, you are going to print two graphs. One is for the final velocity of the projectile and one is for the initial velocity for the projectile. Simply here, where it says graph 1, change the name to a elastic collision. And then write your name. And then go ahead and click on File and print one copy of this graph for you and one copy of this graph for your partner. Then return and select a portion of the graph to get the initial velocity of the projectile and then print graph one more time. Once you're done with this, you're going to follow the steps and then calculate initial momentum, final momentum, and change in the momentum for the case of elastic collision, as well as the initial kinetic energy, final kinetic energy, and the change in kinetic energy for the elastic collision. Once you're done with this part, you're going to analyze the data for the inelastic collision. So you remember run number 2 was a case for inelastic collision when two objects stuck together. So you're going to take for x1 run number 2. So this is a projectile. Enlarge this graph. So now you see you have the data before the collision and then you have the slope after the collision. If you take run number 2 for the x2, which is a data for the target, and graph it on the same graph, you notice that the slope for the blue curve and slope for this orange curve are going to be same because they represent the velocity of the two carts stuck together. So now we are going to click here on the blue curve, select the data that is away from the beginning and away from the point of collision, and then again use the linear fit to obtain the initial velocity for the projectile cart before the collision. Now highlight this run number 2, the orange curve here, and select the data again away from the point of the collision and use the linear fit to obtain the final velocity of the two objects combined together. Okay, now you're going to record this initial velocity for the projectile and final velocity for the projectile and target together to your laboratory manual, and you're going to use this data to calculate the initial kinetic energy, final kinetic energy, fractional change in kinetic energy, as well as the initial momentum, final momentum, change in momentum, and fractional change in the momentum. Before you move any further, you need to print this graph, so name this graph again. So label it as inelastic collision. And then write your name. yours and your partner's name. And now go ahead and print the copy of this graph for you and for your partner. The reason I am being particular about naming these graphs, labeling them for elastic or inelastic collision, is because you're going to need these graphs to study and prepare yourself for the quiz number 4. Also, writing your name on the graph ensures that once you go to pick up your results from the printer, you will pick up your own results. Okay, so now you're done with analyzing the data. Please proceed with instructions in your laboratory manual and answering the questions. Once you're done with the experiment for the day, make sure you leave the station in exactly the same condition you found it when you walked into the lab, as well to close the data studio and log out from the student account. This is all for this week. Thank you.